So let's continue on with domain 4, and now we're going to talk about those network components and some securing of those network components. Now we need a good foundation, so we're going to go over our network components first to make sure we understand what's going on, and we'll sprinkle in some of that security stuff as we go along. So we're going to talk about the operation of the hardware, transmission media, look at some cabling types, network access control devices, some endpoint security, and then wrap it up with content distribution networks. So the operation of our hardware. Let's talk about a hub, a switch, a router, and a load balancer, just to get a good foundation of things you may see out there in the infrastructure. Now a hub is a layer 1 device. All right, this is a piece of hardware. It's a box. It usually has some plugs in it where you plug in your RJ45 connections. Now those connectors are connected to some type of media, and we're going to talk about those guys in just a second. But a hub is, well, for lack of a technical term again, it's a dumb device. It doesn't really do anything except replicate out our signals. Think of it like a power strip. Right? You plug a power strip into the wall, the electricity comes through, and you may have 4 or 5 other ports on there. Well, those 4 or 5 ports all have equal opportunity to that power coming from the wall. A hub kind of does the same thing. You may have 3 or 4 cables plugged into it. Data's coming into one. That hub replicates that signal out to all other active ports. So you may have signal coming in on port 1, and something plugged in on port 2, 3, and 4. So the signal comes in and it gets pushed out 2, 3, and 4, regardless of whoever it's destined for. The hub doesn't care. That's what makes it not such an intelligent piece of hardware for us. Now we used this early on because it helped us with bus topologies. Remember we talked about bus and star topologies earlier, and we said bus topologies, the one with just a single string or single cable, if something was to break or become disconnected, the whole network came down. Well, a hub acts as that terminator now. So where we plug in our systems, if one comes unplugged or a wire breaks or something happens, we don't lose the whole network this way. The hub it doesn't send the signal out there because it's not a live port anymore. So that's where a hub comes into play. Kind of just disseminates out the traffic, and it doesn't care who it's destined for. It just says, oh, I got something coming in. Let me tell everybody else about that. And then it's going to be up to the computer to decide, well, that's not my MAC address, so I'm going to drop this information. So it's not super efficient, but it did its job back in the day. So we had hubs, and we moved on from that where you may have bridges. Because hubs, again, they don't do anything, but bridges, they break up what they call a collision domain, where we can't have everybody talking on the line at the same time. Remember we talked about that carrier sense multi-access collision detection, where I'm listening for the line to see if anybody's talking. If they're not, and somebody else may be listening at the same time, they don't hear anything, we may communicate at the same time and have a data collision. Well, bridges will separate those data collisions. So let's say I have my network here and I've got 8 computers. Well, only one can talk at a time out of the 8. But if I was to put a bridge, which is another type of device, in between those 2 sets of computers, now these 4 could talk, and one of these 4 could talk at the exact same time, because that bridge separates those out. Now let's take that one step further and talk about switches. Because a switch is like a box with a whole bunch of those bridges inside. So every port on a switch is its own collision domain. So that means we shouldn't have as many collisions, if any collisions at all, in a switched network. Now this is a layer 2 device. It could be a layer 3 device, but what I'm mentioning right now is a layer 2 device. It works off MAC addressing. So it has a MAC address table so it knows where the traffic is supposed to go. That's what helps us with our collisions. Remember a hub. It comes in, it blasts it out everywhere. A switch is going to learn where certain computers are. Same for ports. Data's coming in port 1. The switch is going to look at something that it calls its MAC address table or its CAM table. It's going to look and say, okay, I don't have that MAC address, so I'm going to flood it out every active port. And when somebody replies, I'm going to learn that. So let's say computer number 2 on port 2 talks back and says, hey, that was me. I want to talk back to whoever's on port 1. Well, the switch is going to say, oh, I know who's on port 1 because I just learned that information a second ago. So instead of blasting it out all active ports, it's just going to take it and go directly to 1. And now when 1 talks to 2, it will go directly to 2. It won't even bug computers 3 and 4 now, which is great because now 1 and 2 can talk at the exact same time that 3 and 4 can talk, and 5 and 6 could talk. Because everybody's on their separate collision domains, we shouldn't have any collisions this way. Switches are very efficient when it comes to this because now instead of running at like half duplex, which means we can only listen or receive at the same time, say with a hub, with a switch we're running full duplex. We can send and receive traffic at the exact same time. That makes us more efficient. That makes us faster. That makes our networks run faster. Now, there are other benefits to switching on top of the speed, which should be enough for everybody, right? Because that's what we want. Faster, faster, faster. Everybody's talking about faster networks. But switches also can filter out traffic. We can apply filters to say what's allowed and what's not allowed by MAC addressing. So we could do MAC address filtering and say, you cannot connect to this port. And we can use something like port security, which we decide who gets to use that port. We can set up something which they call sticky MAC. And the first computer or device that plugs into that switch, the switch will learn the MAC address and will populate its table and say, okay, only this MAC address can be connected to this port. So if you were to unplug that, and somebody else was to plug into that port, it could shut it off. It could disable that port now because it says, wait a minute, that's the wrong MAC address. You're not allowed on this port. Go away, so it won't pass any traffic. We can do port mirroring as well, which is good for us as security professionals if we're looking for malicious traffic. So what we could do is set up, say, whatever's coming and going on port number 1, we want to mirror that to port 48. And what we could do then is set up a protocol analyzer or some type of traffic monitor on port 48, because everything that's coming and going on port 1, which we may suspect something's going on there, we're getting an exact copy. So this will help us in our analysis, and it will help us in any forensics that we may be doing in our investigation to see if there's any malicious activity on that particular port. Now, we have to get in a switch to do that, or some switches, I should say, to configure that, to turn on port mirroring. So you can switch that information inside so we get the exact copy. Now, sometimes you can get a switch that has a mirrored port on there. And you plug in, say, your IDS or your IPS directly into that port. And that port kind of acts like a hub. So all the traffic that's coming through that switch hits that port as well. So you can hook up your traffic monitor or your traffic analyzer to that port to see, again, if there's any malicious doing going on inside of your network. So that's huge benefits when it comes to switching. Way more benefits in a switching network than in a hub-based network. We don't even use hubs. Don't plug them in. If you have one, put it away or sell it, give it away, something. We want to use switches. A lot more benefits, a lot better security than hubs because, well, hubs offer zero security when it comes to networking. Now, I've talked about collision domains a little bit. I said every port on a switch is its own collision domain, which is important for efficiency, because that means, again, we can talk and listen at the exact same time. So 1 could talk to 4 while 2 was talking to 3, and vice versa, at the same time with no collisions. Now, a collision domain is a group of devices on the same segment. Every port on a switch is the segment, is its own segment. So that's why I can say that every port on a switch is going to be a collision domain. Inside that collision domain, that means only one device on the segment can talk at once. On a hub, the whole hub is a segment, all right? No switch. So everything coming off the router is the segment. On a switch, every wire coming off of a port is a segment, its own collision domain. Now we also have VLANs, and we can use VLANs for security. We use VLANs to segregate traffic as well. A VLAN is a virtual local area network. Now what this means is we're using the same hardware that we have inside of our infrastructure, but virtually or logically we're separating the traffic. That helps, the traffic separation helps with security, and because we're segregating that traffic, we're separating it out inside of the network. So let's think of it this way. Let's say I had a college campus, and I had data traffic, I had VoIP traffic, I've got student data traffic, I've got faculty data traffic, I've got server, my data center traffic, I've got management traffic. I've got all this traffic. Do I want it all on the same pipe? Do I want to cross over my management with my student traffic or my VoIP traffic that's real talky and chattery and needs quality of service? And do I want to mix all this together? Probably not. Right? I could separate this out with VLANs, or I could go buy, however many I just said, 6 different switches, because I've got 6 different categories of traffic: student, faculty, server, VoIP, management, so 5. I could go buy 5 switches, 1 for each category. And then depending on how many buildings I have, I'd have to buy 5 switches for each building. And then I'd have to have 5 routers, 1 for each category of traffic. 5 IDSs or IPSs, 5 firewalls. You're starting to get the picture here, right? Running 5 sets of cables. That's not cost effective, nor is it very efficient for a network and server admin. Because now I've got so much congestion, physical congestion, in my comm closets and my data centers. Not feasible. So we'll use the existing hardware to run all of this traffic, but we're logically going to separate it out, where maybe the VoIP traffic runs on a particular VLAN, which means it's not going to cross with the student VLAN, which won't cross with the faculty VLAN, which won't cross with my server VLAN or my management VLAN. I can keep that traffic separate, and it will help me with my security because I don't have to worry about students seeing particular traffic or faculty seeing particular traffic or trying to mess with the server traffic. Now, for VLANs to work, we're going to need something called a router. Now, you probably have a router in your network already, but this is a layer 3 device. Remember, layer 3, the internet or network layer, depending on which model you're looking at, we're talking about IP addresses, the roadmap of how do we get from here to here. The router separates or brings together, however you want to look at it. If you're a half empty or half full kind of person, it separates or brings together different networks. You have a public network over here possibly, and on this side we have a private network. Well, we'll stick a router in there, remember that gateway of how we get our traffic out of our network out to the public network. Well, this router separates that traffic. Now, routers we can do a couple things with, all right? They route traffic based on destination IP addresses. We can also put security on a router. We can put what they call an access control list, kind of like the same thing we put on a firewall. We can have rules on this router that says traffic coming in from a particular subnet or coming from a particular area or coming into trying to access a particular port is allowed or not allowed. We can deny or permit that information from coming into our network. So that gives us perimeter security. So you can say any subnet coming from this country or region cannot access port 23, 22, 25, 80, 443, 3389, any ports you want to come up with, right? You create those rules, and as soon as it hits that router, the router will look at the criteria that you've set and say, oh, wait, this matches this rule, that's this IP address. Nope, denied, you can't come in. So that gives us that perimeter security, which is very helpful because we can filter it even more as the traffic comes through with, say, different types of firewalls, which we're going to talk about here in a little bit. Something else a router does is it separates broadcast domains. Now, we've talked a lot about collision domains, right, where we can send and receive at the exact same time. But broadcast domains is the limitations of where the broadcast traffic will go. We talked about ARP request earlier, that address resolution protocol. And I said when somebody needs a MAC address, they'll broadcast out. They'll say, hey, I've got this IP address. Who has the MAC address that goes with this? Well, that's broadcast information. That stays on your side of the router because routers by default don't pass broadcast traffic. So that's what makes them separators of our broadcast domain. Every interface on a router is a broadcast domain. So if we had a router and there was an interface here plugged into some Ethernet cable that went to a switch, this is a broadcast domain on this side. We could have the exact same setup over here, and that's a separate broadcast domain. So whatever they're screaming over here, I won't hear them over here. Too many hears. So on this network, they could be broadcasting. I won't hear them on this network, and vice versa. Okay, because that router won't pass that broadcast traffic. So that's how it separates out those broadcast domains. We can also have something called a load balancer. Now this splits the load between devices like servers and routers, and it's supposed to improve performance for our services. Now where this comes in for security could help with DOS attacks or DDoS attacks, because you hit the load balancer first, and it says, okay, I'm load balancing for, like our graphic we have here, for 3 web servers. So instead of all the traffic destined for just one web server, and it has to handle all of those calls and then tie back into maybe an application server and then hit a database server and then come back out, now the traffic hits a load balancer. And he says, okay, you're going to take a little bit, 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 you're going to take a little bit. And he's kind of spreading the love out, right? Everybody gets a little bit of the traffic, or you handle this request, the next request you're going to handle, the next request you're going to handle. So while you're doing this, these two may be idle. But the next thing that comes in, you're going to be doing the work. And the next thing that comes in after that, you're going to be doing the work. So that way we're spreading the love out, hopefully alleviating some of the pressure off of a single device. This could help. And a DOS attack. The load balancer could try to spread the attack around if that's how we want to deal with a DOS attack in the first place. So we've talked about all these devices, switches, routers, hubs, load balancers, but how do we connect all of these devices together? Right? They're not wireless. They're not magic. Can't sit them close enough together so they'll talk. We have to have some type of transmission media. So we're going to look at 3 types of popular cables: coax cable, twisted pair, and fiber optics. Now the first one, let's talk about coax or coaxial cable. This contains a center conductor made of copper that's surrounded by a plastic jacket with a braided shield over it. And you've probably seen these. This coax cable has been around for, well, many, many, many years. If you think about the cable coming into your house from maybe the cable company or your satellite dish provider, right? It's that black, white, it's usually not the orange ones because those are the ones that you can bury outside, but it may be white, maybe black, but you'll see it, right? It's got the little screw thing on the end and that copper thing that pokes out in the middle, right? That's the piece that's carrying the actual signal for you. So you screw that in. Say we used to screw it into the back of the TV. Remember, you screw it into the back of the TV to get the signal into the television, so you could watch TV. But nowadays you can put it into the back of your satellite receiver. You can still put it into the back of some TVs. I have one that comes in that pulls in my ISP's traffic, and I screwed it into the back of my modem, my cable modem that I have. That wire is the coax cable, right? It has that copper prong in the middle, the conductor, and then around it, if you look down in there, or if you've ever cut one, there's a plastic all the way around it, right, that protects it. And then for strength, they put that shield around it, that braided shield, and then they cover it with plastic, like PVC or a Teflon coating to protect that. That's what covers that metal shield and give it that black or white look, whichever kind you get. All right. Now that Teflon type covering is frequently referred to as plenum rated or a plenum rated coating. And what that means is that it passes local regulations when it comes to fire codes. So if we put the cable in walls, in ceilings, right, we can have this cable in there because it's if there is a fire, all right, not when, but if there is a fire in your organization, your building, home, this cable does not give off the toxic fumes that some of the other cables may give off. If you think about businesses and high rises, okay, inside the walls, there's airspace in between there. It's where we run all the cables, maybe from floor to floor or building to, office to office. So we have all these cables in there. Well, if all these cables were to catch fire or start melting and start giving off toxic fumes, it may spread out through the whole building in those air gaps in the air spaces between the walls and between the drop ceiling and the actual ceiling itself or the next floor above you. You know, you may have 18 to 24 inches in there. Well, that's a lot of airspace. If a fire was to happen, toxic fumes could be circulating in there. They could spread throughout the building and cause a lot more damage maybe than the fire does. Could be potential loss of life on some of these toxic fumes if there was enough cabling in there. And you'd be surprised how much cabling they shove in the walls in some of these buildings. You open up the wall, you cut it open or whatever because you have to work on it. You may see a bundle of wire that you can't even get your hands around. And it's running up hundreds of feet and hitting another comm closet, and then you got another 100 and 200 feet, and then another 200. I mean, you'll see all this cabling. So we want to use plenum coatum cables. And it just doesn't have to be coax. They have this in other medias as well that we're getting ready to see. But plenum rated coating, that's usually dictated by local or state fire codes that you have to have that because of those toxic fumes. So that other one I was talking about could be twisted pair. All right, very, very popular. This is multiple individually insulated wires that are twisted together in pairs. Usually we have 4 pairs in there, depending on which one we talk about. But if you're using a Cat 5 or Cat 5e or the Cat 6 cables, stands for Category 5, Category 5 Enhanced, and Category 6, you're going to have 4 pairs inside of this one sheath. And the pairs are actually twisted together. And then, so you have 4 pairs inside of your cabling. 8 wires all together. Now those wires inside, they're individually insulated as well. So they have insulation around them. And then the bundle of wires in there, they have insulation around them also. Now, sometimes we can put a metallic shield around the 8 individual wires and then put the plastic sheath coating around the metal shield. Now, that metal shield is what makes that a shielded twisted pair, which you may see that as STP. It's a little more difficult to work with than UTP, which is unshielded twisted pair. Because of that metal, metallic shield that it has around it, it's obviously going to be harder to cut with tools. It's going to be harder to pull. It weighs more. It's more expensive, but it can protect your data a little bit more than UTP. Because of the shield, it's less susceptible to electromagnetic interference and radio frequency interference. So it's harder to tap into, it's harder to pull data off of those wires. So again, risk analysis, pros and cons of what you need. If you need more security, STP is the way to go if you have to use twisted pair. So like I said, cable without that shielding is called unshielded twisted pair, or UTP. Now it's extremely popular. It's easy to work with. It's relatively cheap when it comes to cabling. You just have to buy the right connectors, and that's the tricky part, right? You get an RJ45 connector that goes on the end, and you clamp it down. That's about the most difficult part there is working with these. You can buy them already made, or like I said, you can custom make them as well. So why are the wires and the cables twisted anyway? You know, I've mentioned that a couple times now. Because when electromagnetic signals are conducted on copper wires, like in close proximity like that, you may get something known as crosstalk. So twisting the 2 wires together as a pair minimizes that interference and can even protect them against interference from, say, outside resources or outside sources. So it's for protection, it's for crosstalk. That's one reason. And then the other one is for protection against outside. Plus, it makes the cabling a little bit stronger when you're pulling it through. All right, if you have something straight opposed to twisted around, that makes the 2 twists a little stronger when you're pulling it, because when you pull cable, you're pulling that cable. You may be pulling it up over a wall and through the ceiling. And sometimes you got to give it a little, put a little elbow grease into it, and you don't want to jerk on it, and you don't want a totally straight wire. You could actually snap that off. So again, a couple different reasons there, but it's for the crosstalk mainly. Now that unshielded twisted pair, like I said, I think it is the most common today. It's cheaper, all right? It is easy to work with, and we do have different categories: 1, 2, 3, 4, 5, 5E, and 6. Now you're probably not going to see 1 through 4. 3 was somewhat popular maybe 15 years ago, 20 years ago, because it was the standard. It's outdated now. 5E and 6 is what we want that can carry the most data. Category 6 can get up to a gig speed. That's pretty good. 5E can get a gig speed as well. Now, those are the ones that you want. 6 it is probably the better of the 2, but 5E can get the job done just as well.